Hi, let's begin this year's lessons by reflecting on the last one. In this episode, I'll discuss my top 5 most favorite discoveries of the James Webb Space Telescope and how they are changing our perception of the universe. And of course, I'll share the essential astronomical details that may help you appreciate them better. Let's begin. Observations indicate that the universe is around 13.7 billion years old, and incredibly, astronomers have now found a galaxy observed just 290 million years after the Big Bang using the Webb Space Telescope. Over the last 2 years, astronomers have used the JWST's capabilities to explore cosmic dawn, the period in the first few 100 million years after the Big Bang where the first galaxies were born. These galaxies provide vital insights into the ways in which the gas, stars, and black holes were changing when the universe was very young. In October 2023 and January 2024, an international team of astronomers used the Webb telescope to observe galaxies as part of the JWST Advanced Deep Extragalactic Survey program, also known as JADES. Using Webb's near-infrared spectrograph called NIRSPEC, scientists obtained a spectrum of a record-breaking galaxy observed only 290 million years after the Big Bang. The spectrum of a distant object is like its barcode. A spectrograph splits the light obtained from an object into its components, which are then used to determine how much has the wavelength stretched since it left the object. In case of this galaxy, known as JADES GSZ140, this corresponds to a redshift of about 14, that is, less than 300 million years after the Big Bang. This image, taken at a wavelength of 15 microns, was taken by MIRI, the mid-infrared instrument on board NASA's James Webb Space Telescope. This is a region near the protostar known as IRAS 23385. IRAS 23385 and IRAS 2A, which is not visible in this image, were targets for a recent research effort by an international team of astronomers who used the Webb telescope to find out that the key ingredients for making potentially habitable worlds are present in early-stage protostars where planets have not even formed yet. This is a very important discovery which helps answer one of the long-standing questions in astrochemistry. For many years, astronomers have wondered about the origin of complex organic molecules in space. The detection of such complex organic molecules in ices suggests that solid-phase chemical reactions on the surfaces of coal dust grains can build complex organic molecules. Some of these organic molecules are the basis of life as we know it on Earth. So scientists are keen to explore that to what extent they are transported to planets at later stages of protostellar evolution. It is possible that these icy complex organic molecules are incorporated into comets and asteroids, which in turn may collide with forming planets, delivering the ingredients for life to flourish. Besides the complex organic molecules, astronomers have discovered simpler molecules such as formic acid, the compound which is responsible for causing the burning sensation of an ant sting, methane, formaldehyde, and sulfur dioxide. This is an important finding too because research suggests that sulfuric compounds like sulfur dioxide play an important role in driving metabolic reactions on Earth in the initial days of evolution of life on the planet. Several complex organic molecules, including those detected in this research, were previously detected only in warm gas phase. Scientists now believe that they originate from the sublimation of ices. Sublimation is the process where a substance directly changes its form from solid to gas without becoming a liquid. The detection of these complex organic molecules in ices gives us hope about improved understanding of the origins of other, even larger molecules in space. This image shows the spectrum of the protostar IRAS-2A, which is in very early stages of evolution and is not forming planets yet. However, Models suggest that this protostar is very close to the early stages of our own solar system. The complex organic molecules detected in this and another protostar IRAS 23385 are therefore very similar to the ones we expect to have seen in a primitive solar system and the debris from which Earth formed. Thanks to the JWST, astronomers have spotted the earliest supermassive black hole blowing a full-scale galaxy-size wind just 700 million years after the Big Bang. This quasar, known as J1007 plus 2115, is the third earliest and the farthest known quasar blowing such a large-scale wind. Basically, a quasar is powered by a supermassive black hole as it accretes dust and gas from its host galaxy. In case of J1007 plus 2115, the outflowing wind is not just the oldest one observed so far, but is moving away from the supermassive black hole with an incredible velocity which is 6,000 times the speed of sound and extends to 2.3 kiloparsec, which is equivalent to 3,750 solar systems lined together. Every year, this wind is shunting off matter equivalent to 3 suns from the galaxy. This implies that by now, that is 13.1 billion years later, the galaxy must have long turned into a red and dead galaxy because it would have lost most of its gas and dust in this outflow. As we discussed earlier, gas and dust are essential for forming stars in a galaxy. Moreover, in this situation, this wind from the central supermassive black hole not just empties out the galaxy but kills its own supplies because it is also fed by this gas and dust itself. WASP 43b is similar in size to Jupiter. It is primarily made up of hydrogen and helium and is much hotter than any of the giant planets in our own solar system. Although its star is smaller and cooler than the Sun, WASP 43b orbits its star at a distance of just 2 million kilometers, which is less than 4% of the distance between Mercury and the Sun. With such a tight orbit, the planet is tidally locked, which means that one side of the planet is continuously illuminated while the other is in permanent darkness. Although the night side never receives any direct radiation from the star, strong eastward winds transport heat around from the day side of the planet to the night side. Since its discovery in 2011, WASP 43b has been observed with numerous telescopes, including the Hubble and now retired Spitzer Space Telescopes, which observe it in the infrared waveband. While the HST images clearly showed the presence of water vapors on the day side, both Hubble and Spitzer images suggested there might be clouds on the night side. In 2024, astronomers used the JWST's mid-infrared instruments to measure light from the WASP 43b system every 10 seconds for more than 24 hours. By observing over the entire orbit, astronomers were able to calculate the temperature of different sides of the planet as they rotated into our view. Scientists then used this information to construct a rough map of temperature across the entire planet. The measurements show that the day side has an average temperature of nearly 1250 degrees Celsius, which is 2300 degrees Fahrenheit, hot enough to forge iron. Meanwhile, the night side is significantly cooler at around 600 degrees Celsius, that is 1100 degrees Fahrenheit. Further analysis shows that the night side on WASP 43b is probably covered in a thick, high layer of clouds that prevent some of the infrared radiation from escaping to space. As a result, the night side, although very hot, looks dimmer and cooler than it would in the absence of clouds. The broad spectrum of mid-infrared light captured by Webb also made it possible to measure the amount of water vapor and methane around the planet. The spectra shows clear signs of water vapors on the night side as well as the day side of the planet, providing additional information about how thick the clouds are and how high they extend in the atmosphere. Surprisingly, the data also shows a distinct lack of methane in its atmosphere. Although the day side is too hot for methane to exist because most of the carbon would be in the form of carbon monoxide, methane should have been detected on the cooler night side. But the fact that methane is not detected implies that WASP-43b must have wind speeds reaching something like 8,000 kilometers per hour, because if wind moves the gas around from the day side to the night side and back again fast enough, there is not enough time for the expected chemical reactions to produce detectable amounts of methane on the night side. This wind-driven mixing leads to the same atmospheric chemistry around the planet WASP-43b. The JWST double-checked the measurements of the expansion rate of the universe by its predecessor, the Hubble Space Telescope, and confirmed that there were no major errors. This adds up to the issue known as the Hubble Tension. Putting it simply, measurements of the expansion rate of the universe is defined by a property called the Hubble constant, which can be measured in different ways. The value of the Hubble constant obtained by JWST and the Hubble Space Telescope observations do not agree with the values obtained from the cosmic microwave background observations, indicating that we don't yet fully understand the universe. The cosmic microwave background is a fairly uniform background radiation which seems to fill the entire universe. It is strongest at a wavelength of around 2.7 microns, which falls in the microwave region of the electromagnetic spectrum. The cosmic microwave background is not associated with any particular object, yet it engulfs all the objects, just like water lilies in a lake. In this analogy, the water in the lake is the cosmic microwave background. The cosmic microwave background is considered as an afterglow left over from the Big Bang and offers a very precise measurement of the rate of expansion of the universe. So when astronomers use the cosmic microwave background measurements to evaluate the rate at which the universe ought to be expanding today, this is almost like viewing the universe in its infancy just around 379,000 years after the Big Bang. The CMB data, together with the standard model of cosmology, suggests that the universe should be expanding at a rate of around 67.8 kilometers per second per megaparsec. But an alternate way of measuring the Hubble constant is through the distance ladder, which we discussed in an earlier video, a link to which is provided in the description below. Basically, each step of the distance ladder is made up of different techniques of measuring distance to objects. As we climb up the distance ladder, we measure distances to farther and farther objects, assuming some model for their standardized luminosity. How bright these objects are can tell us their distances, which we can then compare to their redshift values to determine how much the universe has expanded while their light has been traveling towards us. The problem, however, is that this method gives us a completely different value of the Hubble constant, which is somewhere around 73.2 kilometers per second per megaparsec. This is known as the Hubble tension. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. One possible explanation is that there is a measurement error at the bottom step of the cosmic distance ladder, which is home to the Cepheid variables. Cepheids, as you know, are stars with luminosities that predictably fluctuate as the star's surface pulse in and out. Astronomers have now established that longer is the pulsation period between instances of maximum brightness, greater is the maximum luminosity of Cepheids. This period luminosity relation allows for accurate measurements of the distances to Cepheids. By simply measuring the period of pulsation, astronomers can estimate the maximum brightness, and based on how bright a Cepheid variable star appears in the sky, they then work out how far away it must be to appear that bright. But this is not a foolproof method. The Hubble Space Telescope observed Cepheid variables in distant galaxies, but the more distant they are, the harder they become to distinguish among all the other stars that crowd around them. As such, astronomers were concerned that the unresolved stars adjacent to Cepheid variables in these faraway galaxies were adding to the Cepheid's apparent brightness values, creating an unseen systematic error in their measurements. Interstellar dust can also affect the brightness of Cepheid variables, dimming them from our observations on Earth. But new measurements of 5 galaxies hosting a combined total of more than 1,000 Cepheid variables achieved with the James Webb Space Telescope have ruled out this possible error. The JWST's infrared cameras cut through the interstellar dust, while its greater resolution allows it to clearly resolve the Cepheid variables so that they stand out from the crowd. From these JWST measurements, a team of astronomers led by Nobel laureate Professor Adam Rees determined that HST's original measurements were actually correct. Out of the 5 galaxies observed by the JWST, the most distance is NGC 5468 at around 40 megaparsec from us. This galaxy hosted 8 Type 1a supernovae over the last few decades. These supernovae have a standardizable luminosity curve which form the next step on the cosmic distance ladder above Cepheids. Because the preceding step is required to calibrate the next one, the JWST's observations of Cepheid variables therefore makes the distance measurements using Type 1a supernovae more accurate because they are bright enough to be seen in much more distant galaxies than Cepheids. And they too tell us that there is a contradiction in the different measurements of the Hubble constant taken from the HST and JWST measurements and those from the CMB measurements. So as Professor Rees said, with measurement errors negated, what remains is the real and exciting possibility that we have actually misunderstood the universe. I hope you would have enjoyed this summary of JWST's latest discoveries. Do let us know which one of them intrigued you the most. If you are enjoying our content, please do share it with other astronomy enthusiasts and do not forget to like and subscribe to our channel. I'll see you next week. Until then, take care.